Hello there. Welcome to Calculus Chapter 1, Lecture 3. Today we're going to introduce you to the main focus of Chapter 1, and that is what we call a limit. All right, so let's think back to our bicycle example from Lecture 2. We wanted to find that instantaneous velocity. So in order to find instantaneous, not average, but instantaneous velocity, we need to explore the concept of the limit. All right, so the limit, and I'm going to draw a graph in just a second, is the y value. Okay, so think of a graph. You have your x-axis, your y-axis, so it's the y value that a function approaches. That's the key word. It's one of the key words. A function approaches as you get closer to a particular. So think about this as a graph. We're mapping a function out on a graph, x value. Okay, get a new marker here. We'll draw this out. Okay, so let's say we have a function. X-axis or y-axis, and it doesn't matter how we draw it, just going to do something like that. All right, it's this nice curvy function. All right, and let's talk about right here. So let's say that point on the function, the y value is 7, and the x value is 5. All right, we'll call this function f of x. And we want to think of it as like your hand. So I'm going to draw a terrible. All right, but let's say you're tracing the line with your index fingers. Okay, like this. That's the way you want to test a limit. So the way we say this is the limit as x approaches 5 is 7. Okay? So when I say x approaches 5, I mean the x value, y. So as we get close to 5 on the x-axis, our corresponding y value gets close to 7. So it's where your fingers come together. That's the answer. Now that seems like common sense, right? I mean, come on, why are we going through this? Well, what calculus does is it helps you. Let's say that the function is undefined at 5. Algebra doesn't know how to deal with that. It just gives you an answer of undefined. But in calculus, you can get an answer. So let me write another bullet here, and then I'll erase all this. If the function approaches the same value from both directions. All right, so both directions from the right or from the left. Then the limit of the function is that value. All right, so it can say if your hands come together. All right, so far, kind of common sense, but we have to go through this first. All right. So let's get a little bit fancier with our function. Next bullet is if a function yields different y values as you approach an x value from each side then the limit does not exist. All right, so we're going to use the acronym DNE. All right, so you don't have to write out the whole does not exist, just DNE. Okay, let me draw what I'm talking about here. So again, X, Y. So let's say we have a function that has a break in it. Okay, so at this point 5, there is a break in the function. Let's say that the y value up here at 5 is 7, and down here, let's say that's 4. So if you were to trace this with your fingers, all right, so you're coming from the left, coming from the right, your hands, your index fingers don't come together. There's a break in it, right? So hands stay apart. As x approaches, so the x value approaches 5. So as we get close to 5 here, both directions, your hands stay apart. Therefore, this limit does not exist. Okay, because you don't have the same y value from both sides. All right, the limit does not always match the algebra solution for a function. All right, let me give you some examples here. Let's say xy. Let's say we have a function that has a hole. Now a hole means at that point it's undefined, meaning we get a 0 in the denominator. Let's say this is 5, and at the hole the y value is 6. Well, you actually can get an answer, a calculus answer here. The limit, even though it's undefined, is equal to 6, because your hands come together, your index fingers come together at a particular point. So the limit equals 6 as x approaches 5. However, the algebra solution is undefined. So let's say this. I don't know that this is what it is, but let's say this function is f of x is equal to x minus 2 over x minus 5. So what is f of 5? It's plug in 5, so it'd be 3 over 0. Well, that's undefined, right? Algebra can't give us an answer. However, calculus says the answer, the limit, is 6, because it isn't. Calculus deals with the undefined by saying, well, what is it approaching on each side? Okay? That's the difference between the limit and the algebra solution. All right, let me do another one real quick. Okay, we're under that same bullet. Let's say we have this function, another hole, but I'm going to put a point right there, and let's say that's 5, the x value, this is 2, and at this hole the y value is 6. So the calculus answer would be the limit is equal to 6 as x approaches. So we use an arrow to mean approaches. So as x approaches 5, because that is where our fingers come together on the graph. It's 6. However, the algebra solution is undefined at x equals 5. So this is what we call a piecewise function. So the algebra solution is 2. So what we would say is that f of 5 is equal to 2. But the thing is, the algebra solution doesn't really tell us anything about the function. It tells us that, okay, there's a dot, a filled-in circle here at the point 5, 2. But this function actually is this curve up here that's north of all that. The calculus tells us a lot more about the nuance of the function. It gives us a lot more information than the algebra. Okay, so now let's get into, kind of explained to it with graphs, I'm going to get into the formal definition of the limit. And this looks much worse than it is. All right, so the concept of a limit can be described by expressing it in terms of tiny intervals. Right, tiny intervals, which are mapped around a point. So a point on a graph. Okay. So, all right, let's make a graph here. We'll make a nice curve. We don't have to do this. I'm putting a hole there so that it's a little different than the algebra. All right. And instead of doing actual numbers here, we're going to say the x value is c. And the y value is L for limit. So this is L. All right, and I am going to, my graph, sorry about this. It's kind of getting in the way of what I want to draw, so I'm going to have to fix this. So I'm going to take this function, send it a little more south so that I have room to draw what I want. Okay. All right, let me use a different color here. So I'm going to add on the x-axis delta. So let's say this point is c plus delta. And this point here is c minus delta. Now these are, I'm having to draw it pretty big so you can see it, but delta is tiny. And this would be L plus epsilon, would be this point right here. And I'm going to make a little parenthesis on that to show you that it's contained. And down here, L minus epsilon. So epsilon in math is what is just represents a tiny number. So think of it as like a billionth or something like that. So our nomenclature here is the limit as x approaches c. This is the way we express a limit. As x approaches c of f of x, so of the function, is equal to L. All right, what we just talked about. Our hands come together right here. It's equal to L. And epsilon is a tiny number, okay? And it must be greater than 0 also. Okay, epsilon is a tiny number, so like a billionth or a trillionth, but it's greater than 0. Okay, so the limit as x approaches c of this function f of x is equal to L, the y value where your hands come together, okay, at x. So this is the fancy definition, which is not nearly as bad as it looks, okay, when we do the problems. So if epsilon is greater than 0, okay, this tiny number, epsilon, there exists a delta greater than 0, so a corresponding delta on the x-axis greater than 0, so that for all x, satisfying this interval, 0 is between the absolute value of x minus c. Okay, so what we're saying that for this interval here, we have the absolute value of f of x, the function minus L, is less than epsilon. Okay, so if we have there, if there exists a delta greater than 0, so that for all x satisfying that interval, all right, we have f of x minus L less than epsilon, then the limit as x approaches c of f of x is equal to L. Okay, so we're going to do some problems where we solve for epsilon or delta, but I'm telling you, it's really, really easy. That part is not a problem. The doing the math and answering the question is not a problem. So this is a fancy way of saying what? Okay, so I'm gonna rewrite this definition as follows. Okay, so this is the formal definition. It's important that you learn it in college calculus. They will go over that, but all it means so in other words, points close to L can be found by plugging in right, we're function notation, we plug a number in, points close to C. So if you plug in an x value that's really close to C, you're going to get a y value that's really close to L. That's very understandable, okay? All right, there's no homework associated with Lecture 3. We'll start the homework with Lecture 4, and we'll start working some problems from the book in Lecture 4.